Welcome to Chapter 6, Non-Equilibrium Excess Carrier in Semiconductor. So in this chapter, we discuss the behavior of non-equilibrium. So the keyword here is called non-equilibrium electrons and hole concentration as a function of time and space coordinate. Excess electron in the conduction band and excess hole in the valence band. So you have to know that excess electron where they are in the conduction band and also excess hole in the valence band. They may exist in addition to, this is what we learned in chapter 4, thermal equilibrium concentration when or if an external excitation is applied to the semiconductor. So when you apply something extra to the semiconductor, then it becomes non-equilibrium. So the excess electrons and excess hole do not move independently of each other, which means that they depend on each other lah. They affect each other. So they diffuse, drift, and recombine with the same effective diffusion coefficient, drift mobility, and lifetime. And this phenomena is called ambipolar transport. Let's look at the semiconductor in equilibrium. So you can see here this is how electron holes are generated and how they recombine. So if the electron have enough energy, you will jump to the conduction band, leaving behind a hole here. Alright. So when they loses energy, electron will fall down to the valence band and they will recombine with the hole. So given that thermally generated free electrons and hole must come in pair, when you generate electrons, you also generate holes. So this is the capital G here. N stand for electron. This is called NOT, initial, equals to GPO. And they will also recombine in pair. Alright, generates in pair, recombine in pair. In thermal equilibrium, we can assume that the total number of free electrons and hole is constant, so the rates at which they are being generated must be equal to the rates we are recombining. So what it means that the generation rates for electrons and hole, these two here, are equal with the recombination rates of electrons and hole. Okay, the NO and PO, NO and PO here. Next, when we have external event, when external forces are applied to semiconductor which is in equilibrium, disruption can happen, and this will cause additional electrons and hole pair. So this additional electrons and hole pair is called excess carrier. Excess carrier would be generated at equal rate for electrons and hole. So you have this one here and one there. We call it Gn prime and Gp prime. So now we have Gp prime and Gn prime here. What is Gn prime, Gp prime? So this is the one that we have covered in chapter 4. And then for chapter 6 here, when electrons are in valence band, then suddenly photon is traveling here. So electron will absorb, the excess electron will absorb the photon, and they have enough energy to travel from valence band to the conduction band, thus leaving behind holes down here in valence band and electrons in the conduction band. The number of actual excess electrons and holes are called delta N and delta P. It's given here, delta N and delta P. This one, NO and PO, is the one that we have learned in chapter 4. So now if you plus them up, we will get the total number of free electrons and the total number of free holes. The excess electrons and hole will also recombine in pairs, similar to the Gn prime and Gp prime. So now we have Rn prime and Rp prime. And over here we are writing using capital R. So when they loses energy, electrons will travel from conduction band, drop down to valence band, and they will recombine again. They will recombine in the valence band. So this is the one Next, we'll look at the simple model of recombination. In here, it stated that the probability of electrons hole back recombining is constant with time. So here, this equation here, dn and dt here is the net rate of change in electron concentration. So the rate here must be proportional to both electron concentration and hole concentration. Yeah? Electron concentration and hole concentration. So the net change of in electron concentration is written in here. dNt over dt is equals to alpha r. Then you got ni square. You already know what the ni square. Nt and pt is, the nt here is, which is the thermal equilibrium plus with excess electron, and pt here is the thermal equilibrium hole concentration plus with excess hole. So when you multiply them all together, you get this term here, alpha ni square. It is the thermal equilibrium generation rate. So note that the entire expression in the parentheses will be less than 0, so that the derivative is negative. This should make common sense as the value of NT is decreasing due to recombination. Okay, if you don't understand it, it's okay. We move on to the next one here. So most important thing that you have to know here is the net rate of change of electron concentration is given by this equation, which is proportional to alpha r. Then in the parentheses, you got ni square minus nt and pt. So we know that since NO, this NO here is constant with respect to time, so the derivative can be taken with respect to dn instead of n. So what it means here is that since this equation here, the nt here, in here this equation is this one with respect to time, right? This is independent of time. This is independent of time. So we can write, instead of writing nt here, we replace it with delta n. So this is what it means here. Replace the nt with delta n. Okay, this is replaced with this delta n here. And since the excess electrons and hole are generated and recombined in pairs, so every time when you have generation, you have these electrons, excess electron, they also will have excess hole, right? So you can assume that both are the same. So delta nt is equal to delta pt. So when you expand this one delta nt and delta pt, you can assume them they are the same here. So let's expand them. You expand them, you get NOPO, NO delta p, delta NPO, delta N, and delta P. So the next thing you do is that this one NOPO, you equal it to Ni square. So they both cancel each other. Then you are left with negative NO, delta P, delta N, PO, delta N, delta P. You replace all this delta P with delta N. So I replace this one here, one, and then this one here. So now you get there you get this second this line here, you get NO, delta N, all this thing here. Then you extract out the delta N. In the end, you get this equation lah. Okay, in the end you get this equation. And this is the explanation of this equation that we got. Okay, so they say that we get into that equation, then we want to solve them, but they say it's not easy to solve it. So we have to use some assumption. So the assumption that we use is called low-level injection. So low-level injection is adopted to make it much simpler, to simplify the equation. So what is low-level injection? Low-level injection states that the number of excess carrier is much smaller than the thermal equilibrium values of the majority carrier concentration. So let's look here. What we replaced just now is delta N, right? So for delta N, the material that we're going to use is N-type. This is how Newman do it. When you put delta N here, you are working on a P-type material. So for P-type material, you can assume that P-type material, your excess hole, the excess electrons are very small compared to PO, very small. And also for P-type material, you have more holes than electron, right? So your electron is smaller as well. So you got this, and these two terms here are smaller. So that is why this term here, this equation on the top here, it can be shortened or simplified. So what you do here is that you know that this delta n is very small and NO is very small, so you can cancel this one. And you can cancel this one as well. And then you bring this whole thing down here, bring this whole thing down here, and you get the term down. This is the term here, alpha R delta N TPO. So we can see that the delta NPO term will dominate. This one will dominate, and this one, the other term on the right hand side, can be ignored. So we can approximate this equation to be this one here, down here. So once you get this equation, then you want to find the solution to this equation. So they say that if you solve this one, you know that you can approximate this function. You want to get this function for delta n here, and it is an exponential, this is an exponential decay from the initial excess concentration. You can say that you may find it something like this equation. When you solve it, you want to find the function of this. This is this equation, delta n at 0 here. And then you got exponential negative alpha, and then you got the POT, and you can simplify this further. And they say that you can give it a name called tau n 0 here. So tau n 0 or tau n naught is the excess minority carrier lifetime. So again, this is their lifetime time, and then tau here depend on the excess minority carrier. Given the equation, note that the excess minority carrier lifetime depend on the majority carrier concentration. Yeah, see, the lifetime depends on the majority carrier concentration, because I say that this we are working on p-type, right? So this is majority and this one is the minority here. The excess carrier recombination rates. So when they try to write this again, this is the top equation here. So they say that the recombination rates here is the change in the number of excess carrier DNT. The excess carrier recombination rate Rn is the change of number of excess carrier DNT. So you can write it as, so this equation that you solved just now here, these two, they say that this actually in fact is called delta n T over T n not here. So delta n is the excess minority. Excess minority. This one is the excess minority carrier lifetime, and then this is the excess carrier or recombination rate lah. You get this equation lah. A bit complicated lah. I know this chapter here. The only way to understand all these things is I suggest that if you go back to your Niemann's book here, this is this part here. This is what I explained just now from the top. Please go back and read this one again. All this explanation that I explained to you, and you read all this part here. This is the same one that the solution that I get. So then this is the equation just now. That what you have to know is this one. This is the key important thing here. So for p-type material here, recombination, this is Rm prime and Rp prime, right? So the prime stands for excess. So your excess carrier, you must divide by Tn. See, p-type, so your minority is N here, So delta Nt over Tno. So for a N-type material, you have to use delta, and instead of using N, you have to use P here. Okay, that's the only thing that changed here. This one you use for P-type, you use TNO. For N-type, you use TPO. And what is TPO? Excess minority carrier lifetime. Excess minority carrier lifetime. Okay, so for a P-type here, for an N-type material here, is majority is electron. Minority, who is the minority? Minority is hole, so use P here. So generation rates of excess carrier are not function of electrons and hole concentration. In general, the generation and recombination rate may be a function of space, coordinates, and time. Getting back to our equation here. These are the one here. This is the equation that I explained just now, and that is the expansion. Okay, this is example 1. Okay, now let's look at example 1 on excess carrier. Consider we have a silicon right now, T temperature 300, and then we are doped with donor impurities atom and concentration of 5 times 10 to the power 15. So this should be 15 here. Make sure that you change it to 15. The excess carrier lifetime is 2 times 10 to the power negative 7 second. This is the excess carrier lifetime. So what do we want to find? You want to determine the thermal equilibrium recombination rates of hole. We're going to get hole here. And the second one, we want to get the what is the excess hole recombination rate. Okay, so you see, part A is we're going to find only for holes, but part B is excess hole. So you have to understand the difference between hole and excess hole, right? Do not get confused, because most students, they thought that this is asking the same thing here. No, we are asking recombination rates of hole, and this is asking recombination rates of excess hole. So let's look at the solution here. The first thing you do is that you are given ND equals to 10 ND here, and in the first example that you see is NO equals to ND. And if you recall, in chapter 4, we have this compensated semiconductor equation where this ND minus NA over 2, and then after that you got the square root ND minus NA over 2, then you square them, my plus with NI square there. So if we use that equation, it's similar here, because NA is not given, NA is equal to 0, and this 10 to the power 15 is higher than the intrinsic 10 to the power 10, so we can just assume NO equals to 5 times 10 to the power 15. Then for the PO, how do you solve it? You use the NI square equation. So you take NI square, divide by this NO here, and you get in the end, for your holes, you're getting 4.5 10 to the power 4 here. You get this, and you use this to get your recombination rates. How do you get it? You see RPO equals to, this is the answer that you get. You put it down here, and this, is it given or not? TPO, excess carrier lifetime. Yes, it's given here. The excess carrier lifetime is 10 to the power 10 negative 7. You calculate and you get your answer here. Make sure that if you answer in the rates, you have centimeter negative 3 per second. Okay, let's look at the next one. For the next one, for part B here, delta N and delta P are given. So what do? You just take the delta P, divide by the time, the lifetime, and you divide them, and you get this answer. Fairly straightforward. For example 2, you're looking at gallium arsenide as temperature 300 is uniformly doped with acceptor. Now this question, we change it to acceptor now. That is why you got this Na there. And excess carrier lifetime is 5 times 10 to the power 7, negative 7 second. What do you want to get? We want to get the excess electron hole recombination rate. So you want to get the excess here. If the excess electron is delta N, 5 times 10 to the power 14. And using result A, what is the lifetime of hole? So for this solution is that it's given that you got this delta N, you put it down here, and then you're giving this excess carrier lifetime. You take this one here, just put it down here, you divide them, and you get the answer. Much straightforward. For part B, this is a bit longer here. For part B, you want to get what is the lifetime of holes. So hole, not excess hole. So hole is given as this one, 2 times 10 to the power 16 here. And you divide them, you get NO, and I square divide this, you get NO. So what's the purpose of finding NO? The reason is because of this equation here, where recombination rates for carrier, if you get for holes, hole divide by the lifetime, and O for electrons, you divide by lifetime. So in earlier on, we solve it for NO, you just put it here, NO here, 1.62 here, and we want to get the excess carrier lifetime, no, as the lifetime of holes. We want to get this lifetime of hole here. So you just turn them around. This going to the top, is going to bottom here. This R, okay, R here is NO divided by TNO. This one inverse, you get this, you plug it in. PO is the one that you get on top. PO here. NO, sorry, this is, let me check here. This is going down here, and the top one is going for NO. You divide them and you multiply with the excess carrier lifetime, and you get this answer. So mainly it's just using this equation, make sure that when you replace them with the correct variable. And let's look at example 3 right now. N-type silicon, donor is ND 10 to the power 16, minority whole lifetime to be TPO 20 microsecond. So what you want to do is you want to get the lifetime of majority carrier electron. Okay. Determine the thermal equilibrium generation rate for electrons and hole. Okay, they just want to get for electrons and hole. This one is get generation, that is recombination. So for part A here, very straightforward. You got this. This is your majority carrier electrons, 10 to the power 16. And you use this square, Ni square equation, divide by 10 to the power 16. Then you get this equation here for PO. Then this is the same one here, 10 to the power of 16, NO with TNO, PO with TPO. This is the equation just now you get. You put it plug here. This is from the top here, you put it down here. Then you turn them around left and right hand side. Then you get this answer. Next one, generation rate equals to recombination rate. What do you do? This one 2.25, you want to get and divide by 20. So this is 2.25 where you get this PO. So it's PO divided by TPO. It's the same. And for recombination rate, it's the same as well. Okay, fairly simple. The next thing that we are going to look at is the characteristic of excess carrier. So the characteristic is that we want to know, or we want to model how the excess carrier behave with time and in space in the presence of electric field and density gradient. Electric field, you know, that is related to drift. Density gradient is diffusion. So what is the effective diffusion coefficient and what is the effective mobility that categorizes the behavior of this excess carrier? And to answer this question, what we have to do firstly is you have to develop the continuity equation for the carrier and then develop the ambipolar equation. So the first thing we do is that we're going to get the continuity equation here, and follow up by the ambipolar transport equation. So this is the start of this continuity equation. A lot of this equation here are just substitution, the first order differential. So let's consider the flux of particle in and out of small box. The word flux here is stands for the number of carrier per unit area. So assume that the flow of particle only occur in the 1D along the x-axis. You're going to move from the left to right. And this box is called a differential volume because it's going to change through time. And you're going to see that we're going to move from x to delta to dx here, left to right. And it's a small volume of box here. This box is called a differential volume with the dimension of dx, dy, and dz. So assume our particles are whole. So you do for Fp here. F stands for flux. By using the first order Taylor expansion, by using this Taylor expansion, we just expand them, and now we only expand it to second order. Then we get something like this equation here. So the net increase in particle within the volume will be the difference of the two fluxes at x and at dx, and you minus them up and you multiply by the area, and this is the Taylor expansion based on this part here, and we're going to get something like this equation here. So the net increase in particle inside the box also can be written as delta P over delta T dx dy dz, which is this equation here. Now you can see P here. P stands for the holes, total number of holes that changes with time in that volume. And this is the one that you saw earlier on. This is based on flux. It's also called delta F Pxx over x dx dy dz. So this will represent the buildup or the decrease of particles in the box due to the different flow rates. So once you already solve that, you also need to take account the generation and recombination that we did before, right? The generation and recombination that might be occurring to the box. And these two phenomena also will contribute either in increasing or decreasing the number of particle concentration within the box. Therefore, you have to add, these are the one that we solved earlier on here. This is called the increase in the numbers of hole per unit area, per unit time due to hole flux, and also due to, we have to introduce these two more terms here. This is called the generation of hole. You are familiar with this. We already covered this. Minus with, what is this? This is called the recombination rates, the decrease in the numbers of holes per unit time due to recombination of hole. And the recombination of hole here, because this is P here, we know that there's difference, right? We know that there's P and PO, but this is P. So P, there's a new tau here. It's called tau PT. PT means that the total. So P is the density of hole, and tau PT is the combined whole lifetime. The whole lifetime now, you combine both the thermal equilibrium carrier lifetime, which is the time for PO, and also the time for excess carrier. So you name it as T tau PT. And if you divide all of this equation, the top one with dx, dy, dz, then you'll get this continuity equation. So you can simplify them up, and the changes of a number of holes over time, you get this is the flux here, plus with the generation, you minus with the combination for holes and for electron, and you change this to this negative sign here, and then it's the same lah, fairly same. So the current densities are given by this equation here, J, and current density, right? You know, right? The ampere per unit area is given by this equation here. And if you divide your current density with electron charge here, in fact you can get the flux. So flux, like I told you before, is actually the numbers of carrier per unit area. So what is shown here is that they just divide this by E here, electron charge here, then you get this equation here, which is you get the flux here. If you divide them, you get flux here, and you can cancel out the E here, and you simplify with this equation, you obtain the particle flux, and then you have to take this particle flux, and if you see here, we replace them. So this is this equation just now here, the left hand side, we replace them with the right hand side. Okay, so once you replace it, you get this part here, and you find out that you have P and E here. The function of P and E can be a function of position, so we need to use the differential chain rule. Quite familiar with it, right? E delta P or P delta X. Replace them. So what you do next is you take this and you put it inside there. You take this and you put it inside there. So you get to the next slide here. It's just substitution only. Basically, you substitute, you get this part here. And if you assume a homogeneous semiconductor, what is homogeneous? Homogeneous means that all the doping concentration are uniform throughout the semiconductor. Then you may simplify the total number of carrier again. where you say that the Px here equals to, this is what the thermal equilibrium, and this is the excess carrier and thermal equilibrium excess carrier. So the assumption that they use here is that Px and Nx just become a partial derivative of delta Px and delta Nx, because PO and NO are not the function of time and independent. So instead of using P now and N, you replace this with delta P and delta N in the next slide. So they replace it, replace. So 1, 2, 3. But they do not replace here because this is not differential. They replace again that here 1, 2, 3. The time-dependent diffusion equation has two important terms. The first term is the total concentration given by the red arrow, and the second term is the excess concentration given by the blue arrow. This time-dependent diffusion equation is part of this continuity equation. And if you know that the ambipolar transport that we're going to get in the end is in fact the continuity equation for charge carrier in semiconductor, positive as well as negative charge carrier carries the current in a semiconductor, hence the name ambipolar transport. So before we get into the nitty-gritty derivation step, let me show you the final equation of this ambipolar transport equation. So in this slide, a volume element is shown of a semiconductor with side of dx, dy, and dz. Now let's turn to this ambipolar equation. So the ambipolar equation encapsulates all the possible charge transport phenomena processes in the volume element. So by looking at this equation, the first term that we can see is the time rate change of the carrier concentration. So charge is now flowing in and out of this volume element by drift and diffusion. Inside this volume element, you can see the charge being generated as well as charge recombining. So the same equation can be also applied for hole, leading more or less the same equation, except that the drift term is now negative. So this is a positive for electron, negative for hole, because the opposite effect that the electric field has on positively charged hole compared to negatively charged electron. Now we're back at the derivation of ambipolar transport equation. When we apply electric field, we have to know that there are two components of electric field. The one that the big one, the major one, is called the applied electric field, and the smaller one is called the internal electric field. The applied electric field is from the voltage positive to negative. When within this cell here, we'll find that we have electrons and holes, and that causes an internal electric field from positive to negative. So this internal electric field will create a force attracting the electrons and holes, you can see here, and they will hold them together. So when they hold them together and they start moving from left to right, electrons and hole will then drift and diffuse together with a single effective mobility or diffusion coefficient. And this phenomena is what we call ambipolar diffusion or ambipolar transport. Since electrons and holes are generated in pairs, we can say that the Rn is equals to Rp. And since they are generated in pairs, assuming charge neutrality, we can say that delta N equals to delta P. And we can write the time-dependent diffusion equation that we derived earlier on by replacing delta P with delta N, and we are getting this equation 1 and equation 2. Okay, we're just changing the component inside here to all with delta N. And then we multiply this first equation with mu N, and also the second equation with mu Pp. Okay, we can see on the next slide. So we multiply them together, all this equation here. So after the multiplication, what you do next is you add them element together. So when you add them together, you find that you can cancel this dE, delta E, and delta X. You can cancel this. All right, and you're getting this component here. Okay, see, over here, there are no longer the delta E and delta X component. So after you're done with that, you want to simplify this again. So how do you simplify this again? You divide them by the summation of mu nn and mu pp. So when you did this division, then you get this equation, which you have del d prime and also mu prime. And you see that this is simplified them together. This is the one that what we call a d prime here. You simplify them together, and this is the component where you get the mu n, which is the earlier on. What else? Do you want to simplify this further? Yes, we can simplify this again using Einstein relation that we learned in chapter 5 by using this substitution, the d prime. It becomes something like this. So it's a simplified version. And you have this component. So for a strongly p-type or n-type material under low-level injection, we can still simplify or reduce the component here. So for a p-type semiconductor with low-level injection assumption, we can say that the hole's concentration is larger than the electron concentration. Hole concentration is larger than the excess electron. And then the d prime, you can assume it as to be close to dn. All right, so this d prime here now, so you want to simplify this by using low level injection. You can use this assumption, and this is well. All right, for n-type semiconductor, your NO is larger than your hole. Your NO is larger than your excess electron, and then you get this. This is what you want, and you get this negative here. All right. So once you already completed getting this and that, the one that we did earlier on, we are looking now at the generation and recombination rate. So we have to do simplification of the GNRN and GPRP. So this is what we do in the next slide. In low level injection, we have a very small number of excess carrier. So for generation and recombination, we have a combination of thermal equilibrium generation and recombination, and also excess. Okay, we have the thermal, the NO and PO. We also have the excess. Okay, this is what we can see here. This is the thermal equilibrium. This is the excess. This is thermal equilibrium. This is the excess. However, for thermal equilibrium, we know that the GNON equals to RNO, so you can cancel each other out. Thereby, it can be written for minority electrons in a p-type semiconductor. So you can get something like this here. You bring this down forward, bring it down, and you're getting that. And this is for p-type. For n-type now, similar expression, you're getting something like G minus R and this component. So when you get these two components here, you replace and put it back in the previous. And this is in the end, the ambipolar transport equation, combining all of our ambipolar transport equation substitution. We're getting this. And for p-type semiconductor, you have to note that what we use here is delta N. And for n-type, what do you use here? Delta P. So what is delta N? Excess electron. What is delta P? Excess hole. So this equation states that there is a change in the excess carrier concentration over time because they diffuse away, it's given by the dP, they drift away, given by the mu P, more are generated, given by the G prime, and they recombine, which is this component, two component here. And with that, we have completed the derivation step by step for ambipolar transport equation. Now let's look at this table 6.2 common ambipolar transport equation simplification. This means that the ambipolar transport equation that we saw earlier on can be simplified in this following condition. the time derivative of excess electron and excess hole is 0 in steady state. If we have uniform distribution of excess carrier, then the diffusion rate and multiply with this is equals to 0, and that equals to 0. Similarly, if you have zero electric field, you multiply with 0, that equation becomes 0. If we have no excess carrier generation, G prime equals to 0. And if you have no excess carrier recombination, which means the infinite lifetime, your delta N over TNO equals to 0. So please take note of this important simplification. If I were to ask you question that in steady state, what will happen to the equation, ambipolar transfer equation, then you have to simplify them based on this specification. Okay, the next thing that we're going to look at is called the quasi-Fermi energy level. So let's look a recap back at the thermal equilibrium electrons and hole concentration that we did in chapter 4. We know that we can write it as a function of Fermi energy. So this is about in chapter 4 here. And we can write in terms of Fermi energy when we change this NC here to the intrinsic concentration, Ni. And then this is the equation. If you look at this, the energy band diagram, the EFI is almost in the middle and EF is above, is nearer to the conduction band for electrons for N-type, and then for P-type, the EF is nearer to the valence band. Next thing, we're going to look at the term here, the quasi-Fermi level. The Fermi level is constant, as we know, for a sample under equilibrium. But because of generation and recombination current flowing, we are in non-equilibrium right now. Non-equilibrium is the keyword here, non-equilibrium. So EF is no longer a constant, However, we still want to know or relate the total electrons and hole concentration. This can be done by considering a shift in EF that represent more or less P or N nature of the semiconductor. These new levels are called EFN and EFP. Because why is EFN EFP? Because now we are taking into account the excess electron and then the excess hole. So now the EF now is upgraded it's become EFN and EFP. That's given here. So if the excess carrier are created in a semiconductor, we are no longer in thermal equilibrium, like we mentioned earlier on, and the Fermi energy is strictly no longer defined. And then we have delta N and delta P now, excess electron and hole concentration respectively. Now we can write it as this. First one and the second. So if you look at the energy band diagram, there you go. We have a new line here called EFM, which is nearer to the conduction band, and EFP nearer to the valence band. Now let's look at some example on how we can solve question on quasi-Fermi level. So we consider an N-type semiconductor at T equals 300 with carrier concentration, and O 10 to the power 15, and I is given, silicon, and PO is 10 to the power 5. So we know that this is an N-type because NO is larger than PO. Then in non-equilibrium, we are given the excess carrier concentration, delta N equals to delta P 10 to the power 13. So you see the excess electron is quite high as well. And O is 10 to the power 15, it is 10 to the power 13. So we just use the equation that we are shown earlier on. The Fermi level for thermal equilibrium can be determined by this. Okay, it's straightforward. Just shift them around left hand side, right hand side, you get this answer. And in non-equilibrium, we added this term here, delta N, and we can find that if you take EFN minus EFI, then it is 0.2984. It's just a very small changes. If you look back to the EFI, before this EF, EFI, EFN, EFI. EF, EFI, EFN, EFI. Okay. For EFP minus EFI, you're choosing PO and delta P, you get this answer. Straightforward example 4. Let's look at a more complicated one. Example 5. Okay, example 5, this is like a bit complicated, like for final exam or test 2 type of question. You have an n-type semiconductor, silicon, and this is given. EFN minus EF is given. The value of Ni is given. So what do we want to find? We want to find the excess carrier concentration. Okay, and we want to get this term EFN minus EFI and EFI minus EFP. And you consider that delta N equals to delta P. How do we solve this? Okay, if you look at this, there's a lot of steps. First thing you do is that you have to draw the Venn diagram and you have to write it out. EFN minus EF is equals to EFN minus EFI and EF minus EFI. Okay, EFI. So we are given all these things here. You got this EFI in the middle. Because it's the N type, the EF is here. Then you got the EFN here. And EFP is nearer to the valence band. So you can see the arrow shows here that what we want to find is EFM minus EF is this region. Let's see the second one. EFM minus EFI and EF minus EFI. So if you take this minus with the purple arrow, you're going to get the green color. Move on to the next one. So for N-type, writing back the same equation, and then you put all the equation around here. Just write it down here. And if you get this equation here, if you are getting in ln, if you minus them, it means that you can do an inverse and multiply them. This is what you get here. And then this cancel each other out. And you get this equation. And you just calculate left hand side, right hand side, calculate, move them around. In the end, you get delta N. And delta N is equals to delta P. Then once you get delta N, you can write down the equation that we want to solve, which is this one here, EFN minus EFI. Just put it in here, solve it, you get your answer. And the second one is EFI minus EFP. And delta P plus P naught. But you see your delta P is 2 to the power of 10 to 2 times 10 to the power 14. Your PO, if you take this Ni divide by this NO, you're getting a very small value. So you just can ignore the P here, which is why the P naught is not written here. You calculate and you get this answer here. With that, we end the chapter 6. Thank you.